In this video, we're going to talk about systems of equations, and we're going to begin working with matrices. A linear system of equations can have 0, 1, or an infinite number of solutions. For instance, think of two lines. The lines could be parallel and not intersect, or they might not be parallel and intersect at one point, or they might be parallel and consistent, and in other words, there'd be an infinite number of solutions. Consistent means there's at least one point of intersection. So if they're parallel and consistent, there will be an infinite number of points of intersection. An inconsistent system is a system of equations that has 0 solutions, and a consistent system is a system of equations that has one solution or an infinite number of solutions. Two systems of equations are going to be defined as equivalent if every solution to one system is also a solution to the second system of equations and vice versa. That's not really going to come up in this video too much. But we are going to do a little bit of work with matrices, and we're going to remember elementary row operations, which are that we can multiply an equation by a non-zero constant, we can interchange any pair of equations, and we can add a non-zero multiple of one equation to a second equation to replace the second equation. Now, what's a matrix? Well, a matrix is a very powerful tool in mathematics. For now, we will introduce matrices as a way to organize our solutions, keeping them neat and organized. Also, matrices will help us to see how we can use elementary row operations to solve a system of equations. But matrices have many more uses than this, and there are entire university math courses dedicated to them. Let's solve the following system of equations using a matrix and elementary row operations. Before we do this, I want to point out that I know you don't need matrices to solve these first three examples we're going to do. You do not need matrices, but we're going to use them just to get used to how they work and maybe what it means when we get more zeros than we expected. So, if I was given the system of equations shown, what I would do first is say that I can express 2x plus y equals negative 9 as 2x plus 1y, and then on the other side of the vertical line there, the number negative 9. And x plus 2y equals negative 6 could be expressed as 1x plus 2y, and on the other side of the vertical line, there'd be a negative 6. Now, I'd like for both of these coefficients to be the same. So I'm going to multiply the entire row 2 by 2. I'm not allowed to only multiply that 1 by 2. I have to do it to the whole row. So if I multiply this whole second row by 2, I get 2, 4, negative 12 instead of 1, 2, negative 6. And the first row stays the same. It's still 2, 1, negative 9. Now, what I realize is I can subtract 2 minus 2 and get 0. I can subtract 1 minus 4 and get negative 3. And then I can subtract negative 9 minus negative 12 and get positive 3. Okay? Now, and again, I'm leaving my first row the same. Well, this is very convenient because if you look at that bottom row, the 0, negative 3, 3, that just means negative 3y equals 3, which means y is negative 1. Okay, so remembering that y is negative 1, we then go up to the first row where it says 2x plus y equals negative 9. We plug in the y value of negative 1, and we see that 2x is negative 8, meaning x is negative 4. And what we found out is that there is a solution to the system, and that the solution is negative 4, negative 1. And since there's at least one solution, then this is a consistent system. Okay, but what if we have the system of equations shown there? Well, we can draw our first matrix fairly easily. The first row becomes 3, 4, 8, and the second row is 6, 8, 15. I like to try to eliminate from that first column. It's not necessary to eliminate from that column, but usually that's my default. So I'm going to multiply the first row by 2. And so 3, 4, 8 will become 6, 8, 16. The second row will stay the same, 6, 8, 15. And then we're going to subtract 6 minus 6 to get the 0. But since we subtracted 6 minus 6, we also have to subtract 8 minus 8, which will also be 0. And then subtract 16 minus 15, which will be 1. Now look at that bottom row. That bottom row represents 0x plus 0y equals 1. That's impossible. No matter what value of x you have, 0x will be 0, and no matter what value of y you have, 0y will also be 0. So to say 0x plus 0y equals 1 is impossible, so that means there are no solutions to that system of equations. It's an inconsistent system. Then we look at this system of equations. 5x minus 2y equals 11, and 55x minus 22y equals 121. Well, I can make a matrix as we know how to do. I forgot my little vertical lines on these matrices here, but I'll draw the little vertical lines where they belong. That vertical line means we're augmenting the matrix. And then I look at that first column where there's a 5 and a 55, and I think, you know what, I could multiply that first row, everything by 11. If I do that, 5 negative 2, 11 becomes 55 negative 22 positive 121. Then I can subtract that x column, leave the first row the same, subtract each entry in row 1 minus each entry in row 2. 55 minus 55 is 0, negative 22 minus negative 22 is 0, and 121 minus 121 is 0. Now, my final row becomes all zeros. 0x plus 0y equals 0. We've essentially eliminated that whole row. That adds nothing to our understanding. So in essence, what we really have is one equation with two unknown values. We really only have that first row remaining. 55x minus 22y equals 121. That means we have an infinite number of solutions. Now, what if we have an example with three equations? Well, first thing we're going to do here, we're going to make a 3 by 3 matrix, and we're going to augment it. We're going to bring the 5 and the 32 and the negative 17 over, change the signs. And we're going to now have situations where we'll see that using a matrix specifically is a rather helpful exercise. Okay? So now we write out the matrix as we know how to do. And we want to get one of the columns to have all the same values. And again, my default is usually to focus on the entries in the X column. So there's a 3 and a 2 and a 2. Let's multiply the first row by 2, and the second row by 3, and the third row by 3, and that'll make each coefficient of X be 6. Okay? Now, when we do row 1 minus row 2 and row 1 minus row 3, we'll be able to eliminate the coefficient of x in row 2, and we'll be able to eliminate the coefficient of x in row 3. Okay? So the 6 minus 6 is equal to 0, and 6 minus 6 here is also equal to 0. Negative 8 minus 3 is equal to negative 11, and negative 8 minus negative 9 is equal to 1. And 4 minus negative 21 is 25, and 4 minus 24 is negative 20. Negative 10 minus negative 96 is positive 86, and negative 10 minus 51 is negative 61. Okay? So, we now are going to focus our attention on these two entries right here, where that negative 11 and that 1 are. And just for the next couple slides, trust me on that, we want to get those entries the same. As long as the magnitudes are the same, it doesn't specifically matter if they have different signs. If they have different signs, if we get a negative 11 and a positive 11, we'll just add. If we get a negative 11 and a negative 11, we'll subtract. And so we want to get those the same so that we can eliminate, and you'll see why in a few slides. So let's multiply the last row by 11. When we do that, we'll get the last row to be 0, 11, negative 220, negative 671. And what we'll then be able to do is add. Negative 11 plus 11 will be 0. 25 plus negative 220 will be negative 195. And 86 plus negative 671 will be negative 585. Okay? And that's what we have in our last row. And now, look at that triangle of zeros circled in, shown in red there. That's really a good thing to have, because what we can now do is we can say negative 195z is negative 585. That'll mean z is 3. We'll take that z value of 3, put it in for 25z, and then we'll be able to say negative 11y plus 25 times 3 is 86. That'll help us solve for y, and we'll find out that y is equal to negative 1. And then when we have that y value of negative 1 and that z value of 3, we'll plug those into the first equation and we'll solve for x. It's very convenient. Okay, so at this point we can solve. We're trying to have one row with 2 zeros to the left of the vertical line, and we're trying to have another row with 1 0 to the left of the equal sign, and the 0 should be in the same column as one of the 2 zeros from the previous one. So getting that triangle of zeros accomplishes the goal. Now, as we'll see in later examples, we're often going to get more zeros than just the ones we were trying to get, and the number of zeros that we get has implications for the types of solutions to the system of equations, or even sometimes to the lack of a solution to the system of equations. But like I've been saying a couple times, I usually aim to get the red triangle of zeros in that spot. It's just a bit of a habit with me. So, negative 195z equals negative 585 means z equals 3. Negative 11y plus 25 times 3 equals 86 ultimately means that y is equal to negative 1. Then in the top row, 6x minus 8 times negative 1 plus 4 times 3 equals negative 10 ultimately means that x is equal to negative 5. And so putting all those together, we get one point of intersection of all three of those planes, which is negative 5, negative 1, 3. So what's been happening this whole time is that when we were first given the system of equations, we were given the equations of three different planes, and those three different planes all intersected at one point, and specifically that point was negative 5, negative 1, 3. Now let's do one more question here. Well, like we did in the last question, we want to augment our matrix, so we'll put the constant terms on the right side of the equal sign, and we'll make our matrix. Now I'm looking at that first column there, and there's an 8 and a 6 and a 2, and I say to myself, the lowest common multiple there is 24. So we multiply the first row by 3, and the second row by 4, and the third row by 12. And then we subtract row 1 minus row 2, and row 1 minus row 3. And when we do that, we get the rows shown right here. Okay? Now, we've got an 11 and a negative 69 there. So what we can do is multiply the entire second row by 69 and the entire third row by 11. And if we do that, we get the value shown here. And they're getting pretty big, you can see, like this 230 times 69 became 15,870, and 66 times 11 became 726. So we're getting some pretty big numbers. But what's good about it is that we got these two numbers to be the same. Granted, one's positive and one's negative. But when we add row 2 plus row 3 in our next matrix, we're going to be able to get a 0 entry in that y column. And in so doing, we're going to have the triangle of zeros that we wanted. Now, once we have that triangle of zeros, we're just going to look at what's left over. What's left over in that last row is that 0z equals 16,596. Well, that's not possible, so there are no solutions. So specifically now, just to re-explain it, look at the last row. The last row here means that 0x plus 0y plus 0z equals 16,596. That is not possible, so it's an inconsistent system, and there are no solutions whatsoever. Now, one more example that we have here. We're going to move the constant terms to the other side. So we've got that negative 34, negative 38, and negative 86. We'll move those over to the right-hand side. And we look at that column here with the 9, 9, and 15. The lowest common multiple is 45. So we'll multiply each of the first two rows by 5 and the third row by 3. And now what we're going to do is subtract row 1 minus row 2 and row 1 minus row 3, but not just the x column, all the columns. And when we do that, we get the values shown in front of you. Now, we're happy with the part of it where we've got the two zeros at the bottom of the X column. Ideally, we would like to get um, these two values the same so that we could then add or subtract row 2 and row 3. Now, one way of doing that would be to leave the top row the same, just don't even change it, and then to multiply the second row entirely by 22, and then multiply the third row entirely by 5. And then after we do that, we'll be able to just subtract these two values right here. And when we do that, we get 45, negative 40, negative 25, 170. And we get 0, negative 110, negative 110, and negative 440. And then when we're doing that subtraction of row 2 minus row 3, 0 minus 0 will be 0. Negative 110 minus negative 110 will be 0. Negative 110 minus negative 110 will be 0. And negative 440 minus negative 440 will also be 0. And what will happen is we'll get a last row of 0, 0, 0, and 0. When that happens, that means we have an infinite number of solutions, unless by some strange circumstance the first two planes represented in these first two rows were parallel, but they're not. And if it even helps you, just look at the values we had earlier on. The normal of that first plane is 9, negative 8, negative 5, and the normal of the second plane is 9, negative 7, negative 4. We did not have parallel planes, so we don't have to worry about this last row of all zeros possibly meaning that there's an inconsistent system. What it actually means, because none of our normals were parallel, what it actually means is that that last row of all zeros means that there are an infinite number of solutions. Now, the reason I did it in red here is because if you, we're going to redo this again in a second, but we're not going to do it in such a way that the numbers get bigger, like negative 110 and negative 440. We're going to do it in such a way that the numbers get smaller. For those of you with a good deal of number sense, use that number sense if you have it. What you might recognize, that second row of 0, negative 5, negative 5, negative 20, you can multiply all those entries by 1/5 and get 0, negative 1, negative 1, negative 4. And that third row of 0, negative 22, negative 22, negative 88, again, multiply each of those entries by 1 over 22 and you'll get 0, negative 1, negative 1, negative 4. So that's what I'm explaining here. It might be reasonable to suggest multiplying row 2 by 22 and row 3 by 5 to get the same values in the y columns of row 2 and row 3, making the numbers fairly large. That's what I just did in my handwriting. But on the other hand, with a bit of number sense, we might see that every entry in the second row is divisible by 5. Every entry in the third row is divisible by 22. So you can multiply row 2 by 1/5 and row 3 by 1 over 22, make the numbers a little easier to work with. So that's what we did here. So we're going to end up at the same solution, but getting the numbers to be a little bit smaller, we see we have an opportunity here, since we have a couple of negative ones, to just subtract row 2 minus row 3 and get that triangle of zeros where we wanted it. That last row is now 0x plus 0y plus 0z. That means there are an infinite number of points satisfying the condition, so there are an infinite number of solutions to the system of equations. And then, like I said, the little thing I was saying earlier, technically we need to double check that the top two rows don't represent parallel non-coincident planes, but the normals of those planes aren't parallel. Specifically in the most recent matrix that we have, the 45, negative 40, negative 25 in the last handwritten matrix there, and the 0, negative 1 in row 2, those are not collinear, so it wasn't a concern. That wasn't a case of an inconsistent system. Specifically, what it was a consistent system with an infinite number of solutions. And then for our last example, it's a little bit of a thinker. We want to solve for k such that the system has no solutions, one solution, or an infinite number of solutions. So let's imagine that the equation kx minus 4y equals 10 is entered into the matrix as k negative 4, 10, and the equation negative 2x plus 8y equals negative 20 is entered into the matrix as negative 2, 8, negative 20. We're now going to multiply the top row by 2. That's going to change it from k negative 4, 10 to 2k negative 8, 20. What we're now going to do is we're going to add row 1 plus row 2. Doing that to the x column gives us 2k minus 2. Doing it to the y column gives us negative 8 plus 8, which is 0. And doing it to the far right column gives us 20 plus negative 20, which is 0. Now, you might be curious, why are we eliminating from the y column, not the x column? The reason is there's a variable of k in the x column, so I figured it's going to be easier to to eliminate from the column that doesn't have a variable. So that's why we did that. Now, what I remember is that there's an infinite number of solutions if the final row is all zeros. So that means where I see 2k minus 2, if that's a 0, then that whole final row is zeros. So in other words, if 2k minus 2 equals 0, I have an infinite number of solutions. So little grade 9 math, 2k minus 2 equals 0 means 2k equals 2 means k equals 1. So k equals 1 means an infinite number of solutions. Okay, but what if k doesn't equal 1? Well, if k doesn't equal 1, then what that 2k minus 2 value would be in that last row, that would be a non-zero quantity representing the coefficient of x. So I'd have a non-zero value times x plus 0 times y equaling 0 in the last row. In other words, a non-zero quantity times x would equal 0. That could only happen if x was 0. I could then take that x value of 0 and plug it into the top equation. 2k times x minus 8 times y equals 20. So letting x be 0, I'd get 2k times 0, which would be 0, minus 8y equaling 20. Ultimately, y would be negative 5 over 2. That's only one solution. So specifically, what we're saying here would be that if k wasn't equal to 1, I would get exactly one solution. I would get the solution 0, negative 5 over 2. So to recap, if k equals 1, my final row is all zeros and I have an infinite number of solutions. If k doesn't equal 1, then clearly from the final row, x is 0, bringing it up in the first row, I get y of 5 halves, I get one solution. And so I can state with finality that there's one solution if k doesn't equal 1, there are infinite solutions if k equals 1, and that we've now used up all the possibilities so that it won't be possible for there to be no solutions in this example.